So now I want to talk about the semantics of lettuce with references. All right, so as I mentioned, we no longer have referential transparency when we have these references floating around. So we have to go back and modify all of our evaluation statements, right? Because now we need to keep track of, did something change in our memory, right? Am I looking up an element in my memory? Am I assigning something to that location in memory? So we're going to have to go through and both model memory and talk about how that works, and then also incorporate that into all of our possible evaluation calls. So the main thing is going to be eval, right? Before I took in an expression and an environment. And now there's one extra thing that we have to keep track of, which is the memory, which we're going to call a store. And what should it return? Well, it should return some value and another store. So the idea is this is the memory before executing expression. And this is the memory after. It's not that there's actually different memories floating around, although in our implementation here, there kind of is because of the way that we handle stores. I mean, but in normal programming language world, right, our store is just the random access memory that we can always pull a little bit out of, right? Or maybe a disk on a disk that we can access. So the store is not actually changing, but we want to keep track of the changes that have happened. So we're going to model that by basically having a snapshot of the memory at each stage of our eval. And we'll just be making a new snapshot anytime that changes and passing on that new snapshot. If we percolate back up some recursion, right, we might end up having, we need to keep track of the fact that that store has changed, right? Maybe it changed in each call of the recursion. So once we get out of that, we still have a modified store, and we want to keep track of all of this. So what is a store? Well, I've already sort of drawn a picture before, right? But it's just going to be a sequence of slots that can take values, right? Not all of them have to be filled. And we're going to label them by natural numbers. And this is the basics of what a store should look like, right? And to be able to use a store, we need a couple of fundamental primitive things, right? So we need something that will create a cell, right? So if I want to put a new value in here, I need to know which cell is available for me to use. And we'll just call that thing create cell, which will take in a value and the old store, or the current store, and it's going to return a new store, or the newly updated store with an address, which is the location that we put something in, right? So the idea here is that if I say create cell 15, then it's going to look through here, and our implementation is going to just be whatever is the first cell that's available. So we'll put 15 in here, and then we're going to, right, so before we put 15 in here, this whole thing was old store, right? And then create cell goes in, finds the first open slot, puts 15 in here, and then makes a copy of this whole collection of data, and then returns, which we'll call new store now, right? And we'll return the new store with the address that contains 15. So that's just going to be 1. Right, so that's what we sort of want. That's what we want new or create cell to do. Likewise, what else will we need in order to implement a memory? We'll need a lookup function, right? So we'll have a lookup cell. And what should this do? Well, it's going to look up some memory location, or right, it's going to look up in a store some address. And what should it do? It should return the value that is in that address. Right, this is not modifying the store, so we don't need to return any store from that. But we do want to be able to look up elements, right? I want to be able to say, look up cell in this store, in my new store, right? This was new store, at location 1, and I should get 15 out. And then, well, what else do we need? We need a assign cell, right? We need to be able to change the value at any particular address. So we'll have, we need a store that we're going to be modifying, that we're going to be assigning something to. We have the address that we want to assign it to, right? And the value that we want to put in that address. And this should return a new store, right? The updated snapshot where I have modified my values, right? So if I switch out 15 for 35, I should return a new store with that 35 there. So these are going to be the primitive structures for handling memory, just like we had the primitive methods for handling an environment. And every time we do any sort of evaluation, as you notice here, we've changed the way evaluation works. Before we didn't have any store and there was just a value that would be returned. Now we need to update everything to keep track of the store. So let's look at one of our earliest ones that we did, right? So eval of plus of E1 and E2, right? Under some environment and now with some local store. Well, what do we have to do in order to evaluate this, right? Well, we evaluate E1. Actually, before I do this, I want to give a little example because I think it's useful to sort of see why we actually need to do it this way, right? And this will give us a little sense into how to do this, which is, let's have x be a new ref of 10 in assign ref of x20 plus dref of x. Right, so here I have a sum of two different expressions. And what's going on here, right? So x is a new ref, so I'm going to find a location over here, pop 10 into it. And then assuming I'm reading left to right, right, what do? I'm going to assign 20 to that location, right, instead. And then I'm going to deref x, which points to this location memory. And so this is going to be 20. And remember, assign ref always returns the value that we assign there. So this is also 20. So this whole thing evaluates to 40. Which seems a little weird, right? Because if we did the evaluation the other direction, right? So imagine we work from right to left in our evaluation structure. Well, x would be a new ref of 10, right? And then we would evaluate dref of x, which would just be 10. And then we do an assign ref, change the value of x to 20, and that returns 20. So if we worked right to left in our plus semantics, then we would have a different answer. Of course, we do write in English and we go left to right, so that's generally how we're going to do this evaluation. But you notice what the issue here is, right? That when I evaled E1, the left-hand side of my plus statement, it changed what happened in my eval of E2. Right, so I need to make sure to write that into my rules here. Right, so I'm going to eval E1. I need to eval it under the environment and the store. And what should I get back? Well, I should get a value and a store, right? So I'm going to call that V1 and store 1. And V1 should be, a real number if we're going to be adding them together. So that takes care of the left hand. Right now I also need to eval E2 in the environment, and what should my store be that I evaluated under, or evaluated with? Yeah, it should be store 1, right? Exactly for this reason, that the store that I evaluated assigned ref under, and then this returns a new store, right, store 1, where x has been bound to 20 instead of 10. And so when we evaluate E2, we need to make sure to evaluate under the store that this guy returned. So we're going to eval E2 under and store 1, and that's going to give us V2 and store 2. right? And this should be a real number if we're not going to have an error case. And then what should this be? Well, it needs to return a value in a store, so the value is going to be v1 plus v2, and the store should be, well, whatever the store ends up being at the end of evaluating my second parameter, right? It should be the final store after doing all of the little in-between bits. And so this new plus rule, right, plus OK, properly handles side effects in our language, right? Because the only side effects we can have is changing references around. And this makes sure that we are tracking all of the possible changes to the store and using the proper store at each time. Let's, so that's how we do plus. Let's look at another example. All right, let's look at eval of our let statements. All right, so what did let take in? It took in a string, took in an expression which we're going to bind to the string. Sorry, let's give these names as opposed to types. All right, so I have string s, I have what it's going to bind to, each e1, and then the body of the let expression, right, after the end, called e2. And this is going to need to be evaluated under an environment and with the local store. We want that to equal something. So what do we have to go through? Well, we're going to have to first evaluate e1, right? Eval e1 under the environment and the store. All right, that's going to give me some value v1 and a new store. And now I need to evaluate e2 after updating the environment to include the mapping s to v1. Right, so now I'm going to do eval e2 under, well, what's my new environment? It's going to be this extend of s v1 env. Right, so I've just tacked down that new mapping on the front of my environment. And then which store do I need to use in order to do this body, right? Well, I want to use store 1. That way, in case during my variable assignment, right, I might have modified the store, right? I might have had something like let x equal assign ref of y to 15, right? Where y was a new ref somewhere above, right? And so in this binding, I want to make sure that when I do E1 here, right, I update the store. And so when I evaluate the body here, where I maybe just say look at y, right, I am doing that with the proper store. And so what should this equal? This is going to be some other value v2 and the value of and the store that returns, right? So it's going to be store 2. As remember, all evals now return some snapshot of the current store. So then this whole eval is going to evaluate to v2 store 2. Okay, so those are some examples of how we're going to have to extend the rest of our language, right? So we're going to have to go through and modify each one of our rules that we currently have to update it to handle the stores like this. It's not too much work, right? Basically, we're just going to keep on, every time we evaluate something, we get a different possible store out. So we want to make sure that the next thing we evaluate is done with that new store. So let's see how, or what the semantics for new ref, deref, and assign ref are, now that we've seen how we need to update everything else. And I'm going to be using these create cells, lookup cell, and assign cells. So I'm going to leave those out there for now. All right, so let's do new ref, right? So if I eval something that looks like new ref, right? What did new ref take in? It took in some expression e, which is going to be which we want to evaluate, and that'll give us a value that we're going to stick into the store here. And so this is under some environment and with some current store. And what do we need to do? Well, we need to evaluate e to begin with. Eval e under the environment with the store. And that's going to return some value v1 with the new store, store1. Right? And now what do we need to do? Well, we need to look up a place to put this in our store and get that address and then return that address, right? We want to come up with a new reference. Oh, this is something I need to mention before we sort of get here, which I've talked about before, but it's important that it's clear, right? So what are our values in our program, right? We have our abstract syntax that we had here, but now what are the values, right? So we had numbers, right? That was our R. We had booleans, B. We had the error term. We had closures, which are C, right, for functions. Now we're going to add references, right? So this is going to be a type that looks like this. It's reference with some address in it, which, yeah, maybe I'll call capital P for pointers. So, right, what is new ref going to do? It should return this as a value, some sort of reference with an address. So we need to come up with what is the address. All right, so let's go back here. We have new ref with E in environment and store. So we're going to evaluate E to figure out what do we actually want to put in our store. That's v1. Maybe it changed the store a little bit, so we want to make sure that we now know what the current store looks like, right? Not the store we started with, but the current one. And now I want to create cell. So I'm going to call, let's call this v2 and store 2. Well, I'm gonna write it as our normal structure, right? So we call eval, we get this as a return. So now I want to call create cell with v1 and store1, and that's going to return, right, a reference, or it's going to return an address, which is going to be in the form of a reference. We'll do it this way, address with store2. And then what is my final eval going to be? Well, I want it to return a reference to this address and store2. Obviously, we've updated store, so store2 is very important here. All right, so this seems pretty straightforward. To make a new ref with some value, some expression for some value, we evaluate that expression, we get a value out, and then we create a new cell in our store, put that value there, and get an address back. And new ref should give us this value, right? A reference to that address. Okay, what about deref? Right, deref, that had an expression in it, right? And we're going to do it under environment in a store. This expression should be a pointer, so it should be of the form reference of some address, right? So the first thing we need to do is figure out what is that address. So we're going to eval E under the environment and the store, and that should be v1 and store1, where v1 has this form, right? It's a reference to some address. Okay, given that, right, I want to look up cell in my store1, right? E could be a complex expression that does a bunch of things and then returns a reference. So it might have modified the store. We can't be certain, right? So we want to make sure to look up our cell and our store one, and what address do we want to use? Well, this address, right? The address that was wrapped around the wrapped inside of the reference that E resolved to. So we have store one, address. And what does lookup cell return? I removed it here, right? But it should return just the value that's there. So let's call that v2. Right? Lookup doesn't modify the store at all. All it does is look up a address and returns the value that's there. So this entire thing, right? The whole point of deref is to find out the value that's in that proper address and that location. So we're going to return v2 and store 1. Right, notice, yeah, because we didn't, lookup cell does not modify the store, we can use the same store there. Obviously, if v1 is not a reference, then we want to throw an error. But this is our error-free deref definition. Okay, and then obviously, what's the last eval we want to write? It's for assign ref. Right, so assign ref, what did we have? We had a right, a string. Sorry, we have, right, expressions. This first one should resolve to an ident. Right, that's the pointer of, say, ident, like x, that kind of thing. This should be whatever we want to store in the location that x points to. Right, so given under, with an environment and a store. Right, what's this going to do? Well, first of all, we need to figure out what the first expression is. I should give these names. Right, now types. So we have E1, E2 under environment and store. Eval of E1, right, under the environment and store. Right, this is going to give us V1 and another store 1. And we want to make sure that V1 is equal to a some reference type, right, to address. Right, this will happen if we have in our environment something like ident of, right, x pointing to ref of address. Right, because then what happens when we evaluate this, we see the rule for eval ident, and that just looks up, is there a value of x in my environment, and it should point to the reference of a reference type, and that reference type will be what we return. All right, so we'll have v1 needs to be of the form reference to an address. Okay, so now we need to eval e2 under the environment and the second, or store 1, right? Cool. And that is going to be what? The value that we want to assign to the location at address. So we want to get that back as v2 and store 2. Right, because maybe it modifies the store as we go through. And again, right, this should be, hopefully there's no errors going on through there. But we're writing down the rule for the error-free form, right? And so what should this final deal be? Well, we have this assign cell, right? So I have a store that I need to put in. So I'm going to do assign cell. What's the store I want to use? Well, the last store that might have gotten modified, store 2. What's the address? Well, that's the address I got from v1 here, right? I can unwrap it from the reference and just get the address straight out. And then the value that I want to assign there, which is v2. right? And what does assign cell return? The assign cell, right? It should return value and the new store, right? New store. So this thing will also, right? This will turn into v2 and then store 3. Sorry, yeah, that's correct. So this is our semantics for explicit references in Lattice, right? We've figured out how do we take a new ref, how do we deref something, and then also how do we look up an element in here and then modify it. Using this basic framework for to model memory, right? Where we can create a cell, we can look up a cell, and we can assign cell. And we just have taken our component parts and connected them together, right? Hope this you could follow this easily. Next, we'll talk about how do we do references without having to actually handle references ourselves.